So this one is another SN2 reaction, and Blakely, you just have to go back and watch the video if that's all right. So this is another SN2 reaction. Again, you're diagnosing a problem. You're using all the skills you've developed so far, but now the nucleophile and electrophiles are changing. So this says, in the synthesis of alkynes, there can be two means to synthesize an alkyne. In either way, there is an electrophile, the molecule bearing the leaving group, and the nucleophile. That is an sp hybridized carbanion. So a carbanion, it's a carbon anion, so a carbon bearing a lone pair, which is overall negative charge. Given these facts, which of the following is the best set of conditions to prepare this compound? So you're given the choices here, A, B, C, or D. These are all reactions, and you're asked to pick which one is going to give you this as the product. My first question to you before we delve too deep, this is showing a triple bond, even though it might not look like it. What's the name of this alkyne? Just as a review. So I see some correct answers in there. Again, the major functional group is the alkyne. Let's count the carbons. We're going to count so that the alkyne gets the lowest locant number. So 1, 2, 3, 4, 5, 6. So we have 2 hexyne or hex 2-ine, as Ian says. I think either can be sort of correct. My preference is more for like 2 hexyne rather than hex 2-ine, because it just sort of reading it makes it flow a little bit better. Again, and as a nomenclature review, we're giving the 2 is the locant to the triple bond, so it gets the lowest number, as opposed to numbering 1, 2, 3, 4. 4 hexyne would be wrong. So the reason I wanted you to do that is because that is important when you're counting the carbons of the electrophile and the nucleophile, because one of these has a miscount, and therefore you can eliminate it as a distractor. So when you consider that, what do we think the best answer is? And again, we're doing SN2, where the nucleophile is a carbon anion, carbanion. So Blakely's eliminated D, presumably because in D, as in dog, there are no good nucleophiles. Everything in D is neutral. Remember, a common sort of formula for a nucleophile, you have a metal cation and then some sort of anion. So yeah, if we look at A, B, and C, we can see that the common denominator of them is this, right? This is the same in all of them, so that's your nucleophile. It would be a nucleophile derived from 1, 2, 3, so propyne. So that's the negative charge, the sodium counterion's the same. Now what you're differentiating is the count in the electrophile. These are all bromines, but only one of them is going to have the correct count to get you your hex sign. So if you can, another skill, sort of what Aiden and Ian have alluded to, another skill is visually with your eyes mapping. When you look at this carbanion, you see methyl, then the triple bond. Now look here, you see methyl and then the triple bond. So really, the bond that you're making, so this is supplied here. So you're making this bond right there. So if this is the negative charge, this thing over here has to be the positive. So you need 1, 2, 3, and you count 1, 2, 3. A is the correct answer. Here you count 1, 2. That's not right. 1, 2, 3, 4. That's not right. So that's a simple counting exercise. So in the prompt here, I said there are two means. This problem is showing you one way. What's another way to make this molecule where we dissect the nucleophile electrophile differently? So what I mean by dissect, this is the dissection point between 3 and 4. What two other carbon compounds could we use to make this? One's going to be an alkyne, so in the chat, put the name of the alkyne. One's going to be an alkane, put the name of the alkane. We're looking for the other pair. So I just wrote on there that this is called an internal alkyne. The triple bond is within basically the way that's defined. Here's your triple bond. You have a carbon and a carbon substituent. A terminal alkyne is basically one of these is going to have a hydrogen. So really, to rephrase my question, I'm looking for a terminal alkyne and an alkane. The alkyne becomes the nucleophile after it's deprotonated. The alkane is the electrophile. So I'll give you another minute or so to consider putting in the name of that alkyne, the name of the alkane before I put it on the slide. Anybody got a guess? So Aiden, you're kind of so Aiden, you're sort of answering the question that's already there. So what do I mean by that? So if we're looking originally at this dissection, yes, this is propyne, and then this would be the 1-bromopropane. So this is making this compound one way. I want you to consider making it an alternative way using a different starting alkyne and a different starting alkane. So you're making this bond between 3 and 4. Let me sort of back up. If we're making the bond between 3 and 4 this way, If we want to make it the other way, what carbon-carbon bond are we making? Just put 2 numbers in the chat. Pick 2 carbon atoms. No, Blakely, you want to include the alkyne already in one of the starting materials. So Aiden says 1 and 2. That's correct. We want the alternative method, so I'll use green. We want to make that bond. So the alternative pair would be 1-pentyne and, say, methyl iodide. So here's your 1, 2, 3, 4, 5, 1-pentyne and methyl iodide. Again, Blakely, this is just a thought exercise to help you practice about what these problems are. I'm telling you, when you make alkynes, you can make them 2 ways. The problem originally is asking you one way to do it, and then I'm asking you what is the other way to do it. It's a thought exercise if you understand sort of the scenarios involved. So let's just move on from there. So here is our review of SN2. Again, SN2 stands for substitution nucleophilic bimolecular. The nucleophile attacks at a trajectory of 180 degrees to the leaving group. The lone pairs of the nucleophile, which is the Lewis base. So lone pairs of nucleophile attack the sigma star orbital of the leaving group. That bonding pair of electrons goes here. This bonding pair then leaves with the leaving group. The hybridization changes to sp2 hybridized. This is a transition state, the most fleeting non-isolable species. There's that 180 degrees. You're going to see the inversion happen here. That has to do with the stereochemistry. Then your leaving group then ends up with those electrons. So what I'd like to get into is the nature of the leaving group in the solvent today. So here again as a review, all sorts of nucleophiles that you can use. You want to use these because you make different functional groups, as we've seen here. Here are their names. And then you can think about how you would identify those in IR or proton or carbon NMR. So the nature of the leaving group, as we said, alkyl halides are typically used. So we know from chapter 10, I know we went out of order, but I have a flow in the logic of how I teach this course. You learned about alkanes, CC-CH bonds, nonpolar. We then moved to chapter 10, CH substitution via radical reaction. That gets the halogen in the molecule. The molecule then becomes polarized. We can then use that as a good leaving group. So then we're now back to chapter 7 to do these other functional group transformations. So let me write down why halogens, a reason why they're good leaving groups. So it's you know, from a first approximation, yes, there is some memorization, for lack of a different word, of teaching this, but we really want to understand the why. And you know, not to get on my bully pulpit here, but you're in college, in the university experience, not to memorize stuff, but to become a thinker. So you want to think about things and explain why they are. So here are the halogens. This is the periodic trend: fluorine, chlorine, bromine, iodine. So what are those distances to carbon halogen bonds? So these are in angstroms. So you can see clearly that as you go down the halogen series, the bond length increases. So as a trend as well, for just the halogen itself, the van der Waals atomic radii, so the halogens from fluorine to chlorine to bromine to iodine get bigger, right? That helps explain why the distance between the carbon atom gets longer, because there's less orbital overlap. So now, knowing that, in this trend between fluorine, chlorine, bromine, and iodine, how would you say the leaving group ability going down that series, going down from fluorine, chlorine, bromine, iodine? Does the leaving group ability get better or worse as you go from fluorine to iodine? So Max says it gets better. So why does it get better? What's a reason why? So I don't really so I would say larger is a better explanation, and so Aiden is cluing in on it. Heavier really isn't the best explanation. So think about what's happening in the mechanism, right? As the nucleophile attacks and the leaving group leaves, you're sort of you're cleaving this bond, right? So in the comparison of 1.38 versus 2.11, if that bond is already longer, it's further away from the carbon anyway. So that makes it a really good leaving group, because it's not as strong a bond as, say, the CF bond is. And so all these things come into play that you learned from Gen Chem. The iodine's really huge. It has poor orbital overlap with carbon to begin with. It's further away. So it's more polarized. It wants to leave anyway. And so when it does leave, it's able to stabilize the negative charge better as well. So we can use all of these explanations. So halogens are really good leaving groups. You know, the leaving group ability. So we increase down this trend. And again, just to rephrase that, if you want to do an SN2 reaction, you want to do iodine before bromine, before chlorine, before fluorine. So if we wrote that in a trend, And as we'll see, fluorine itself, it really is not a good leaving group because the bond is pretty stabilized. So if you think of, does anyone cook? You cook at home? For instance, do you make scrambled eggs or any sort of omelets or anything? Chances are if you have like a pan that's coated like with a black coating, that black coating is typically Teflon. And Teflon is a perfluorinated polymer. What that means is there's a lot of CF bonds, and so that fluorinated surface basically makes the pan non-stick. So when you make your egg, it doesn't stick to the pan, it just slides right off and you can slop it on the plate. So CF bonds are pretty stable. F is not a good leaving group. What I do want to talk about are some other leaving groups that you're going to see. So let me back up, get my nomenclature right. So sulfonate esters. We know that sulfuric acid is a pretty strong acid. So when it reacts with water, water acts as the base. It's leveled. So water is a leveling solvent. You form hydronium plus the conjugate base of sulfuric acid, which bears the negative charge. Put another way, this is really stabilized, and it's stabilized through resonance or conjugation. So what is a resonance arrow? That negative charge can migrate. So by stabilizing that negative charge, it's a good leaving group. So we as human beings, scientists, chemists, have taken that behavior and transformed sulfuric acid in derivatives called sulfonate esters. And sulfonate esters come from alcohols. So if we start with an alcohol, we can transform it into something that's a good leaving group to do SN2 chemistry. So what might that look like overall? Say we're starting with our methyl bromide up here. We're going to treat that with sodium hydroxide and water to make methanol. The OH group is a terrible leaving group, so methanol is a really bad electrophile for SN2 chemistry. The reason for that, if you were to break this CO bond, you would get hydroxide as a leaving group. And if we look at pKa's, we see that water itself is an acid, has the pKa of 16. Its conjugate base is not really stabilized. So when we're talking about good leaving groups, again, we're at pKa's of 0 and negative. So this OH would be a bad leaving group, so we have to transform it into something else. So the conditions we use for that, one of the compounds is the following. This is called methane sulfonyl chloride. So if you recall, you learned about acid chlorides. Basically, this is a sulfur version of it, so sulfonyl chloride. Within that, we're going to have a base. So this molecule here, triethylamine, that's a base. And then we can use a solvent, say dichloromethane. And the reason we have these conditions, the base, the solvent obviously solubilizes everything. Look here, HCl, that generates HCl, which is neutralized by the base. We form a bond between this oxygen and that sulfur to form the following compound. We've neutralized the HCl as the ammonium salt. So now this portion of the molecule here, that's your leaving group. This is called methyl sulfonate, or it's abbreviated mesyl, or MS. So organic chemists like to use a lot of abbreviations, so that's what those things mean when you come across them in your book. And so this hopefully you can see the pattern. You have this oxygen, the sulfur double bonded to oxygen, sulfur double bonded to oxygen. So it's not exactly sulfuric acid like sulfate, because you're missing that fourth oxygen, but this is a good leaving group, because when it does leave, that oxygen is, the negative charge is stabilized through resonance from here to there and there. So yeah, this thing here is called, it's a salt. So the analogy I like to teach when I do this, you know about sodium chloride, Na plus Cl minus. So look, you have the same anion, right? Now this cation is different. Plus, instead of sodium, you have triethylammonium. This is inorganic. This would be an organic salt. So again, that's moving on from Gen Chem to organic. You know, the themes are still the same. So now this is a good leaving group. OH is not a good leaving group. We've transformed it into a good leaving group. So just as a quick review before we go on to the next slide, we have an alkane, no good leaving groups. We do radical substitution. We now put a bromine in, or chlorine. We have a good leaving group. We can take sodium hydroxide, do a substitution, get this OH. The OH is a bad leaving group, but we can activate it with this species to make this, which is a good leaving group, called a methane sulfonyl ester. It doesn't matter as long as, Blakely, as long as we balance out the plus with the minus, you can write this however you want. So just as a review of those leaving groups, where do we see them on this chart of acidity? So we said I minus, BrCl, that follows that trend. This species right here is the one we just saw. R, SO3 minus, where R can be basically any group. They're using the phenyl ring. We just saw where R is methyl. So again, the leaving group ability, you're really looking at a pK of 0 to negative because these conjugate bases are stabilized. So yeah, when you're threading all this together, if the acid of the conjugate base is really strong, that means it's a really good leaving group. So the next slide, what I want to do is talk about the nature of the solvent, because solvent does play a role in it. It does help you diagnose SN2 versus SN1. So let me just write some solvents down and explain why these particular solvents are used. So dimethyl sulfoxide is abbreviated DMSO. So yeah, maybe over here is where I'll write the actual structure. So for SN2, all of these solvents are polar aprotic, and they have relatively large dielectric constants. So dimethyl sulfoxide, dimethyl form amide, that's DMF, dielectric constant of 37. Acetonitrile, dielectric constant of 36. Again, what we mean by polar aprotic, they all have polarized bonds. Aprotic, they do not have acidic hydrogens, and that being defined as a hydrogen bonded to a heteroatom. So dimethyl form amide, AMIDE. Another one that's sort of common, hexamethyl phosphoric, triamide, HMPT, dielectric constant of 30. Now this one's pretty exotic, but it's basically a phosphoric acid derivative. And then finally, another one is acetone or propanone. So this doesn't have an abbreviation, but the dielectric constant is 21. So these are common solvents used in SN2. So why are they preferred? Remember that the nucleophiles typically have that structure, a metal cation plus a nucleophile that's negatively charged to balance out. So again, this is an example to use that previous nomenclature. this is an example of a salt. These are salts. That's what it's defined as. So how do these solvents help? So remember in the mechanism, the nucleophile, the lone pairs, must be available to bond. This lone pair must be available to bond, so it attacks the sigma star. If you have this, which is really stabilized, plus minus, this is an ionic bond. How do we weaken the ionic bond? These solvents help to do that in the following fashion. So you have your metal plus, say we're using DMF. So this is DMF, dimethylformamide. Remember, the solvent is sort of the pool, if you will, and you're in the pool. When you're in a pool, the water is always touching you, right? So even though I can't draw it, what you need to visualize here, if this is you and this is the pool, the water's always touching you. So around this metal cation, all of these lone pairs of these oxygens on the carbonyl, they're solvating. That's what these lines mean. They're solvating this. So that helps to weaken this bond. It frees up the nucleophile to attack. So these solvents help to solvate the metal cation, allowing the nucleophile to participate. So we are seeking solvation through polar aprotic solvents. Is that clear for everyone? So again, we're talking about SN2. Why is ethanol not a good solvent for SN2? So the opposite. What happens if you use a polar protic solvent? You have this OH bond. The lone pair of the nucleophile is solvated by this, see this polarized bond here, this polarized OH bond? And how the H has a positive. The lone pair is solvated by that. Again, I can't draw it, but imagine this nucleophile is completely surrounded by solvent. So if that happens, the nucleophile is not available to participate. So because the metal cation is just a spectator anyway, we want to sort of distract it, allow the nucleophile to react. So these are more appropriate, whereas polar protic is not. So let's get on to the meat of this, where we need to diagnose whether it will occur through SN2 and SN1. And now I know that I have not talked completely about SN1 yet, but you know enough about SN2 that you can diagnose these and determine, okay, that looks SN2 enough that I'll go with that. So let's start with 930, and this is from your workbook. Problem 930 is on page 155. So let me ask you a series of questions. We look at this molecule. We only see one polarized bond, delta minus, delta plus. That's the polarized bond. That's the dipole moment. Is chlorine a decent leaving group? Chlorine's a decent leaving group. How do you classify this alkyl halide? Is it methyl? Is it primary, secondary, tertiary? So our next question in the diagnosis is the alkyl halide, is it methyl, is it primary, is it secondary, is it tertiary? So it's secondary. So we are within reason of SN2. Again, secondaries are sort of the bifurcation where we can go SN2 or SN1. So now we have to ask additional questions. We have this nucleophile. If you're like, what the hell is that? Just think of, this is hydroxide, right? OH minus. Sulfur is right below oxygen in those groups. They tend to have this similar reactivity. So we have SH minus. Again, think of it, even though they're not showing it, let's just put a counter ion in there. Say it was sodium. Now, is that a good nucleophile? So again, good nucleophiles, typically they're salts. The nucleophilic component has a lone pair of electrons, which this does. So that would be a good nucleophile. DME, I did not show on the prior slide. DME is dimethoxyethane, DME. So there's dimethoxyethane. Is dimethoxyethane polar aprotic? Yes, it's polar aprotic. So that's a good solvent. So far we're clicking all the boxes for SN2. This is our nucleophile. That's our leaving group. The nucleophile, again, is the Lewis base, supplies the electrons to attack. We cleave that bond. We do the substitution. This whole thing stays the same. Nothing changes in that ring. We're substituting Cl for SH. And our byproduct would be sodium chloride. Blakely, sodium is not an electrophile. It is the metal cation that balances out the negative charge in the salt that is supplying the nucleophile. So knowing everything you know about SN2, look at 931. Do you think 931 as written is a good SN2 reaction? So Mac and Cole, Aiden all say no. Tell me one reason why it is not good for SN2. We're gonna list multiple reasons, but tell me one. Okay, it's tertiary, so that's the biggest clue right there. The leaving group is tertiary, so that immediately tells you you have to go to SN1. Water is polar, but what's another reason why? When we're only given this, right? We don't have a separate nucleophile listed, so the nucleophile and the solvent are the same. So how is water different than what we saw up here, where this actually contained the nucleophile? So water is your nucleophile and your solvent. It is not a good nucleophile, so it's a poor nucleophile. Why is that? It's neutral. So think about the mechanism. It's neutral to begin with, so as it proceeds through, it's going to get a positive charge on it. Whereas up here, you're starting negative, and as it proceeds through, it's becoming neutral. So again, those are different dimensions of describing this. So if this does not proceed through SN2, it proceeds through SN1, which means the reaction still substitutes Cl for OH, but the mechanism by which that happens is different. So again, Cl is substituted for OH. This is your byproduct. And what we will do on Monday is we'll talk about how the mechanism for SN1 differs from SN2, and we'll run through the rest of these as well. Again, you have an exam coming up next Friday. It's going to be on 6, 10, and 7. Your chapters, the same format as you've seen for the first 3. I strongly encourage you to do your homeworks between now and then. If you have any questions, shoot me an email. I'll respond with a video. I sent Kaylee a video of her question last night. Hopefully that worked out. But other than that, we'll see you Monday.